So let's talk a little bit about units of measure. We talked about physical quantities, and we talked about dimensions. But all we talked about was length and time and mass and energy and power and velocity and acceleration and things like that. We didn't talk about what units we're going to be measuring in. Mostly, SI, or the metric system, SI stands for System International. It's written SI because in French, it's kind of French, and it's System International, and so, but we would call it the international system, but it's the metric system, right? And so for length we use meters, right? For time we use seconds. For mass we use kilograms. There are English versions of these. We can use inches or feet or miles for length. We can use minutes. Well, we both use seconds, but this could be measured in minutes or hours or weeks or months or years, and we'll do some of that. You can use things besides kilograms. First of all, you can use grams, the prefixes we'll get to in a little bit. You could also use slugs or pounds mass for English, for American or English units, or stones. The British use stones, and so there are lots of different units of mass. Tons mass. But for most of our problems, we use the SI system because it's all base 10. And a kilogram is 1,000 grams. A kilometer is 1,000 meters. A microsecond is a millionth of a second. A millisecond is a thousandth of a second. A milligram is a thousandth of a gram. A centimeter is a hundredth of a meter, and so on. You should know those prefixes. You can look them up. You can Google them or look them up. You should know most of them up to, say, a billion or a billionth. Near 0 and 1, they go in powers of, like, you can have a millimeter or a centimeter, a hundredth of a meter. You can have a meter or a kilometer. But if you want to go more than that, a mega is 10 to the 6th. It's a million. Giga is 10 to the 9th, or a billion, that prefix. Tera is a trillion. If you go the other way, a microgram is a millionth of a gram. A nanogram is a billionth of a gram, and a picogram is a trillionth of a gram. So you can go in either direction. So you should know the prefixes, but the metric system makes it easy because you can stick the prefixes on anything, and they mean the same thing. So I'll tell you a little bit about the history of these. Let me just erase some of this. So if we start out with the second. So we already know that there's 60 seconds per minute, 60 minutes per hour, and 24 hours per day, right? If we multiply all these together, I can cancel the minutes and the hours, and I'll get, if I multiply all that, I get 86, sorry. If I multiply 60 by 60 by 24, I get 86,400 seconds per day. Those two are, 86,400 seconds is 1 day. And that's how the second was defined, as 86,400 of a day. The problem is the length of a day varies because the Earth's orbit around the sun isn't exactly circular, and so the motion of the Earth is a little more complicated than just exactly 24 hours for every rotation. And so what they do is they take an average day over the course of a year, and they define a second as an 86,400th of what we call a mean solar day. So 1 second is equal to 1 mean solar day over 86,400. And that's fine until you want to start doing stuff that's really, really precise. And so when that started happening, they needed a more precise definition for a second. And so the next thing they did was they said, I got to copy this down because I can't remember, 192, 631, 770. 9,192,631,770 vibrations of a transition in cesium. Doesn't really matter. It was, instead of being tied to some complicated thing of the Earth, it is now defined by some a transition in a cesium atom. And so this tied a second down. This gave it a well-defined quantity. So you could send somebody this information on Alpha Centauri or some distant galaxy, and they can go find a cesium atom and count that many number of oscillations to say, okay, that's what their second is. Whereas it would be much more complicated for them to figure out what a mean solar day was. We're always trying to make these things depend on things that are easily measured, or at least measurable, in a systematic way. And so we've actually don't use this definition anymore. And so on the next slide, I'll talk a little bit about how the second is measured, how the meter is measured, a little bit about history of meter, and how the kilogram is measured. So we're going to talk about the definition of a meter. We've already defined a second. And so the speed of light, this is the speed of light in SI units by definition. That is to say, we define the speed of light to be 299,792,458 meters per second. And this definition defines what a meter is. If you go out and measure how far light travels in 1 over 299,729,458 of a second, that's what a meter is. And so light travels 1 meter in this many seconds. And so calling this the speed of light defines a meter for us now. That's how a meter is defined. A kilogram originally, sometime in 1790, it was equal to the mass of 1 liter of water. That was definition of a kilogram. You had to define a liter. We won't talk about that right now, based on distances. The second definition of a liter was they made some lumps of platinum, some kind of compound of platinum, that were kept in Paris and Washington, D.C., and maybe some other places. I think there was one at the Bureau of Standards in Gaithersburg, Maryland. And these were defined as a kilogram. So it was originally this. They made a more precise definition with this, and they made less accurate copies of it. And now it's defined by Planck's constant. Planck's constant is a constant like the speed of light. It depends on, it's just a property of the universe, and its value is 6.626070015 times 10 to the minus 34, and its units are kilogram meters squared per second. We've already defined what a meter in a second is, and so this defines a kilogram. As of 2019, for those of you who have watched the show Stranger Things, this number plays a role. It's like a password or something like that in Stranger Things. I don't think they use these exact numbers, or maybe they do. I can't remember. But this number plays a role in that movie. It's Planck's constant. It's a property of the universe. It can be measured just like the speed of light can be measured. And so if you take the definition we gave earlier for the second, and then you measure this, you get meters, and then if you measure this quantity, you can determine what kilograms are. And so this bases our meters, seconds, and kilograms on things that are measurable properties of the universe, and not subjective things or less easily measured things. Again, the mass of a kilogram was originally defined as the mass of a liter of water. As technology infiltrates our world more and more, we need more and more precise definitions. Originally, the definition of a meter, I'll just erase some of this. Also around 1790, so the same time the kilogram was a liter of water, 1 meter was 1 over 10 million times the distance from the North Pole the French measured this distance by surveying. As time has gone on, we've gotten more and more precise definitions, and so now we have a pretty good agreement on what a second is, what a meter is, and what a kilogram is, and that's good because everybody can then measure them for themselves. They're based on properties of the universe, basically. A second is measured based on a cesium atom. Anybody can get one of those. The speed of light, anybody can measure the speed of light, and similarly, anybody can measure Planck's constant. And so those define what a second, a meter, and a kilogram are. So I'll just talk some units for a few minutes. And we'll start with SI, but maybe I'll say and English. So, for SI, suppose we do length, so SI in English. We're going to do meters and, feet. This could be inches or yards or miles or so on, right? We've already said time is seconds in both, and then we said mass is kilograms, and this is usually, there are a bunch of that you can use. Slugs is one, but usually we use pounds mass. But there's also things like force. Here we use newtons, here we use pounds. Energy, we might use here joules. And this could be, BTUs or foot-pounds or something like that. That stands for British thermal units. we'll mostly be looking at these. We could do a power. This is in watts, and this is in maybe horsepower. Could be BTUs per second, and so on. And so mostly we'll use these, but we'll have to convert back and forth between these once in a while. So unit conversion. So I'm traveling 20 miles per hour. What is this in meters per second? Right? And so the way I do these, and I'm just recommending a procedure for you. If you've already got a procedure that works, that really works, systematically works, because these things are going to get really complicated as the semester goes along, by all means use it. But if you don't have a system that your positive works, like you didn't learn it in a chemistry class or something like that, find one that does. This is what I do. So I might start out with this. I might start out with 20 miles per hour equals, I'll just start out with a statement that's true, 20 miles per hour. And now I want to convert this to meters per second, right? And so, well, I need a relationship between miles and meters, and I can go look it up, right? I can find out that 1 mile equals 1,609 meters, approximately, right? And so that means that that if I divide both sides by a mile, that means that if I divide this side by a mile and this side by a mile, that means that 1 on the left-hand side is equal to 1609 meters per mile. Hopefully that's still on the screen. And so, since these two statements are by definition equal, if I want to keep them equal, I can only multiply one or the other sides by the number 1 unless I multiply them both by the same number. So I can't just arbitrarily multiply the right-hand side by 7 and keep my equal sign. If I want to multiply it by something, I have to multiply it by something that's equal to 1. And so I have to come up with something that's equal to 1, and what I do is I take 1609 meters over 1 mile. Because I know those two things are equal, and so this is equal to 1. Now, this equality has not been changed because I've multiplied this equation by 1. And so this gives me, if I multiply that out, this gives me 32,180 meters per hour. These two have to still be equal because all I've done is multiply this thing by 1 to get that. Right? And so now I want to multiply this by something to get to get my hours to seconds. And so I can just sort of work this out if I want. I can say, look, I want to convert, let's say I want to go to minutes, right? Well, I want to cancel this unit and replace it with minutes, so I'm going to put an hour up here. And then this thing has to be equal to 1, so I'm going to put whatever an hour is equal to in minutes here. I'm going to put 60 minutes there. And now I have so I'll just rewrite this down here. 20 miles per hour is now equal to, and so my hours are going to cancel. Here my miles canceled, right? here my hours cancel, and I get 32180 divided by 60, which is 536.3 equals 536.3 meters per minute. Right? That's what 60 divided, that's what 32,180. And now I want to get that to seconds, and so once again, I'm going to put something that's equal to 1, and I'm going to put a minute here, because I want the numerator to cancel the denominator, so my minutes go away, and I'm going to put 60 seconds here. Meters per second. And so that's how I go between miles per hour and meters per second. When I'm changing units, anytime I'm changing units, I have to make sure that I'm multiplying whatever side of the equation I'm changing by 1. I always like to start out with a statement that I know is true, and then I can keep multiplying by 1 as many times as I want, as long as I know it's 1. 1,609 meters is exactly equal to a mile, so this is 1, or close enough to our precision. An hour and 60 minutes are the same thing, so this parentheses is 1. A minute and 60 seconds are the same thing, so this parentheses is 1. Each time I've multiplied the thing on the right hand side by 1, so I haven't changed its value, and so now I know that 20 miles per hour is the same thing as 8.94 meters per second. This is an example of unit conversion, and we'll use this a lot over the course of the semester. So suppose I want to know how many times does a heart beat in 70 years, right? We'll just talk about averages. And so I might say what we usually know is the rate of a heartbeat is about 70 beats per minute, right? And so I can just say 70 beats per minute, and now I want to multiply this by things that'll convert it into 70 years. And so I'll say I want to cancel the minutes and get hours, and I'm going to work my way up to years. And so 60 minutes per hour, right? This is 1. Right? And that cancels the minutes unit, right? And now I have 70 times 60, which is 4,200. We'll multiply them all at the end, right? And I can say, well, look, 24 hours per day, right?